Now I will demonstrate to you for the circuit that we had discussed till now, how to get the input-output relationship by application of the old second balance. So let us take this buck converter circuit which we have discussed, and let me mark this current I0. I0 is the output current that flows through the output load resistor R0. The voltage across the output is V0. Vi is the voltage of the unregulated input. Now the inductor. So when you want to apply the volt second balance, you have to look for the inductor or the coil in the circuit and take the voltage across that coil. So you go to the inductor, take the voltage across that and mark that VL. Look at the way I have put the arrow. What it basically means is that when you are making a measurement using a physical device or virtually, you are to mentally keep the common of the probe here and the measurement probe on this side. That's what the arrow mark indicates. So I could as well have used the arrow mark on this fashion, which means that if the arrow is pointing on to the right, then you keep the common of the probe on the left and use the measurement probe on the right. But here what I am doing is I am keeping the common probe here and the measurement probe here. So let us also mark the time periods for which PT1 is on and time period for which PT2 is on or PT1 is off, which is 1 minus dTs. Let us also put a graph here indicating that will indicate the wave shape of the voltage waveform, the inductance, and let us divide the time scale in this fashion. I will call this period as dTs, time period during which PT1 is on, 1 minus dTs, time period during which PT2 is on, dTs again the second cycle starts, and 1 minus dTs. So these are the time periods. Now let us look at the voltage waveform across the inductor. So during the dTs period, the pole is connected to T1 and Vp is equal to Vi. On this side of the inductor, in the steady state, this is V0. So in the steady state, the capacitor would have charged up. We are talking of steady state conditions only because we want to have the steady state input output relationship, and during that time we know the volt second balance occurs across the inductor voltage. So this is V0 here and this is Vi here during the dTs period. So therefore I will say it is constant Vi minus V0 during that time, the voltage across the inductor. Then during the time 1 minus dTs, P is connected to T2. So this is grounded. The inductor is freewheeling. So let us say the voltage here is 0. Vp is 0, but V0 is there because V0 doesn't discharge so quickly. We are talking of a switching cycle. So minus V0 appears across the inductance. So it has to be minus voltage here because then only volt second balance will occur. So you will see minus V0 appearing across that. Then again during the next cycle dTs, P is connected to T1, you have Vi minus V0, and during 1 minus dTs time when P is connected to T2, you have minus V0 appearing across the inductor. So this is the inductor current wave shape, and during this time, what is the volt second? This is a rectangular voltage. No need to do integral. You can find out the area just by the height into the time width. So we have Vi minus V0 into dTs. So let us calculate the volt second balance across the inductor. So during this time, Vi into V0 into dTs is the area of this rectangle. Now the other rectangle is this, which is minus V0 into 1 minus dTs. So that is minus V0 into 1 minus dTs. Now that should be equal to 0. These two should add up to 0, or basically what it means is these two should cancel each other. So here I can I can remove this TS. So the remaining portions, if I simplify, you see V naught into D, and you have a minus V naught into 1 minus D. If you take it to the other side, they become V naught into D plus 1 minus D. So basically it becomes 1. And in this side you are having Vi into D. So if you do the algebraic simplification, you will get V naught is equal to Vi into D, and that is the input-output relationship. Now to get the input-output current relationship, you can use the amp-second balance. Average current flowing through C is equal to 0. But for that you have to understand the waveforms, the currents that go through, which we have not yet come to that point. However, you can do the amp-second balance. Later on I will show you how the amp-second balance also work, but I have an easier method for you right now. So let us say I will define this as I, and let us find the input-output current relationship. So to find the input-output current relationship, I will make use of the fact that the efficiency of the circuit is 100%, meaning there is no lossy component within. So Pi is Vi into I, and P naught is V naught into I naught, and I am assuming efficiency is 100%, no loss within. So in such a case, P naught is equal to Pi, or V naught I naught is equal to Vi I. Now I know the input-output voltage relationship here. So let me apply it here. V naught, I will replace it by Vi into D. So you have Vi into D into I naught equals Vi into II. So remove Vi, they cancel off, and you have I input current is equal to I naught into D. So this is the input-output current relationship. You can get it through the capacitance's amp-second balance also, but that is sometime later after we know how the current waveform is through the capacitor. But for now you can use the power relationship or the power balance relationship, knowing that there are no dissipative components. Switch is either off or on, no dissipation here, the ideal sense. Inductance is an energy storage device, no dissipation. Capacitance is a storage device, potential storage device, no dissipation again. So all these components are dissipationless devices in the ideal sense. Therefore, if I take 100% efficiency, I will get this input-output current relationship, knowing the input-output voltage relationship. So this is the formal way of using the volt-second balance across the inductor to get the input-output voltage relationship, and you can use it for any circuit, however complex it is.